Hello and welcome back. Today we'll be getting into section 12.1 on sequences. These are pretty fun to work with. I think you'll enjoy these. So for sequences, generally our domain will be assumed to be n, natural numbers. I think it's common for authors to call them the positive integers, but that's exactly what natural numbers are. So a little bit of the notation. Usually we would use some set notation here. So set of all a sub n, and then we describe how to create members of the set. So for example, 2 over n squared would be a sequence that we would look at. So then look at what some of the elements would be. A sub 1 would just be 2 over 1 squared, or 2. A sub 2, 2 over 2 squared, 2/4 is a half. A sub 3, 2 over 3 squared, 2/9, nothing we could do with that. A sub 4, 2 over 4 squared, 2/16 is an eighth, and so on. What we call the general term is just saying, okay, how are each of these constructed? That would be a sub n is 2 over n squared. So just the general term, sometimes called the nth term. So sometimes they may give us the start of a sequence and ask us to sort of write up what the general term would look like. So we might have something like -1, positive 1/2, -1/3, positive 1/4, -1/5, and we're told that that just keeps going forever. So hopefully you notice that the denominators are just the n. So this is our first, second, third, fourth, and fifth terms respectively. So we name this guy n, we'll name, or a sub n, we'll call this guy b sub n. Our denominator is just going to be the n by itself. So our numerator, we have to figure out, work with the signs. So notice all of our odd indices, first term, third term, fifth term, etc., are going to be negative. Even indices, 2, 4, etc., are going to be positive. That sounds like -1 to a power, specifically to the n. If we were looking at them, I'll just write it up real quick. If we had instead of 1, a -1/2, positive 1/3, -1/4, positive 1/5, and so on forever. And we'll call that c sub n then. We can just call it -1 to the n plus 1 power over n. So that way, odd index, odd plus 1 is even. -1 to an even power is a 1. Kicks us over to a positive. But an even index, even plus 1 is odd. -1 to an odd power stays negative. Here's one section where those of you that have taken stats before might have a slight temporary edge on factorials. If you have not gotten to play with those before, definition n factorial is just n by n minus 1, n minus 2, all the way down to times 3 times 2 times 1. N here is going to be in the set of whole numbers or non-negative integers. So 0, 1, 2, 3, etc. And a couple definitions. 0 factorial is defined to be 1. 1 factorial is just the 1 by itself. Since it said keep multiplying until you reach a 1, 1 factorial, you're already at a 1. So this one is the only one that doesn't really fit the pattern, but this is just by definition. So a lot of the formulas that we rely on working with factorials don't work without this definition being made. So we just agree that 0 factorial is going to be defined to be worth a 1. And you may also notice that, for example, n plus 1 factorial, you can call that n plus 1 by n minus 1 by n minus 2, all the way down to times 3 times 2 times 1. Well, notice this much of it is n factorial, so n plus 1 factorial is n plus 1 by n factorial. So we can always do that if they're asking us to simplify. They give us maybe, let's say, 8 factorial over 5 factorial times, we'll do 4 factorial. I can just expand that 8 out until I hit whatever the bigger these two numbers is. And then I'll expand out the little number. So 5 factorial over 5 factorial is 1. Goodbye to those guys. 8 and a 4 times 2 are the same. And finally 6 thirds is a 2, so this is worth 14. So you should be able to work those out by hand if you're asked to simplify these. And you may even just be given one number on its own, like 5 factorial, 5 by 4 by 3 by 2 by 1. So that's 20 by 6, 120 would be one example. Factorials do get very large very fast. 6 factorial, we're all the way up to 720. 7 factorial, we're into the thousands already then. So the next thing we look at are recursive sequences. Recursive, they'll give you maybe 1, 2, or 3 of the starting terms, and then some relationship saying, okay, here's how the rest of them are built based on what's already there. So this one will say u sub n is u sub n minus 2 plus u sub n minus 1. So we have all the ingredients defined. Let's say the next several terms. So u sub 3 is u sub 1. So n minus 2, 3 minus 2 is 1. So u1 plus u2. So 3 is our n. 3 minus 1 is 2. So 0 plus 1 equals 1. So then u4 is u2 plus u3. u2 we just had written down here. That was one of our givens. And u3 we just figured out was a 1. So there's a 2. u sub 5. So that would be u sub 3 plus u sub 4. So u3 was a 1. u4 was a 2. u6, 2 plus 3, 5 there. u7 then, 3 plus 5, 8, and we'll just finish. We can squeeze through 10 on here, so then 5 plus 8, 13, u9, 8 plus 13, so that's 21, u10, 13 plus 21, 34. If we have a sequence and we're asked to add up the terms of it, technically that's then a series. They introduce us to summation notation in this section as well. So if we have term 1 plus term 2 plus term 3 plus the nth term, capital sigma is saying we're adding stuff up. The bottom says, okay, where did we start? So we'll start at 1. The top says, where do we end? We ended at n. And then middle part says, okay, well, what did we do each time? So for example, if they want us to go from 1 to n of -1 to the k plus 1 times k factorial to show what that would look like. So then -1 to the starting at 1, so 1 plus 1 is 2, times k factorial, we're starting at 1, so 1 factorial, plus, and we do it again, -1 to the, we're on the second term, so 2 plus 1, 3 for an exponent, k by itself, so 2 factorial, -1 to the fourth, 3 factorial, -1 to the fifth, 4 factorial, and so on. And then our general term, I ran out of room there, my apologies, -1 to the n plus 1 times n factorial. So this would be the expanded version of the summation. So a couple of properties of summations. We have a constant times a sub k. So c here is some real number. Well, that's c times a1 plus c times a sub 2 plus c times a sub 3 plus c times a sub n. Well, notice c was present in each one of those, so that's also equal to c times a1 plus a2 plus a3 plus plus a sub n. Well, this is just the sum of a sub k. So sum from k equals 1 to n of c a sub k is c times sum from k equals 1 to n of a sub k. So in other words, we can pull a constant out from a sum. Addition subtraction works just the way you would expect. We can put them together or split them apart. If we're going for in sum, starting at k equals j plus 1 to n, we can find the total sum Should add an index there, my apologies, a sub k. So this is the total if we started at 1. And then we subtract off the stuff that we didn't want. So from 1 up through j we didn't want. So find the grand total. Subtract 1, 2, 3 up to j, since they wanted us to start at j plus 1. So some formulas that we get to play with. The first two of these formulas, those I'll expect you to learn. They're fairly intuitive. The next two, I'm just going to ask that you be able to work with the formula. So sum from k equals 1 to n of just a constant. So we don't have any a sub k involved here. So just some real number. So just some constant. We just have a bunch of c's added together. Well, exactly how many? 1 through n. We have n of those. So that's just nc. Or cn, whichever order you pick. Next one, we'll look at our sum from k equals 1 to n of k itself. So basically 1 plus 2 plus 3 plus 4, etc. For this one, we'll get to the formula in a second. Deriving it, we'll call s our sum of 1 plus 2 plus 3 plus dot dot dot. Plus, now it ends at n, so we also have an n minus 2, we have an n minus 1, and it ends at n. That's not the only way I could write the sum, though. I could write it backwards. Maybe we could start at n and count down. So this is another of the sort of famous mathematical fairy tales. Famous mathematician Gauss, as a schoolboy, was asked to add the first 100 numbers together. His class was being unruly, annoying the teacher. The teacher said, okay, well, that'll keep him busy for a while, so do 1 plus 2 plus 3 plus 4 and tell me the grand total of the first 100 numbers. And supposedly Gauss figured this out in about 5 minutes time. So 2s is, well, look at what happens to each pair. This is n plus 1. 2 plus n minus 1. N minus 1 plus 2 is another n plus 1. 3 plus n minus 2. 3 minus 2 plus 3 is another n plus 1. All of these guys are turning into n plus 1s. And we're going from 1 to n. There are n pairs. So 2s is n by n plus 1. So s is n by n plus 1 over 2. So sum from k equals 1 to n of k is n by n plus 1 over 2. So if we do the famous Gauss example, then sum from k equals 1 to 100 of k, it'll be 100 by 101 over 2. So 50 by 101, 5050. A lot faster than 1 plus 2 plus 3 plus 4 plus 5 and stopping when you hit 100. Okay, so those two, I expect you to just kind of get to know them. The next two, just be given the formula and be able to work with it. Again, we're adding from k equals 1 to n, k squared. That one we're not going to run through the proof of it. For time, we're just going to go ahead and work with the formula. Similarly, k equals 1 to n of k cubed. We're just going to work with the formula. We're not going to derive it. N by n plus 1 squared over 2 squared. So for example, they might give us from k equals 1 to 5 of 6k. Well, then that's 6 times the sum from k equals 1 to 5, since it's c times a sub n of k. So then 6 by, and then this is our n by n plus 1 over 2. So n is 5, so 5 by 6 over 2. So that is worth 90. So let's try k equals 1 through 8 of k squared minus 3. So I'm going to ask you to pause it and give that one a try. Unpause it when you're done. Okay, welcome back. So this one we got to play with a couple properties. First, we can split it up. K equals 1 to 8 of k squared minus sum from k equals 1 to 8 of 3. So top guy, we're following this formula. So then the k here, or n here rather, is 8. So I have 8 by 8 plus 1 by 2 times 8 plus 1 all over 6 minus, and then this is just cn, 8 by 3. So 8 by 9 by 17 over 6 minus 24. And that'll land us at $1.80. Alright, so in 12.1, I would recommend 11 to 81 on the odds, and I'll try to construct something similar on the MyMathLab. If you have questions, please get in touch. Otherwise, I'll see you next time. Stay safe out there.